Hello students, this lesson is on trigonometric equations. Find all solutions to the trig equation that are in the given interval. Confirm with technology. Okay, so our goal here is to find all angles x that satisfy this equation and that are in this interval. So x must range from 0 to 2 pi. That's one complete rotation counterclockwise around the unit circle. Let's begin by isolating the tangent squared. I'm going to subtract 4 from both sides, divide by 3, and then take a square root, which gives me plus or minus the square root of 1/3. Now I can square root the 1 and square root the 3 separately. Square root of 1 is 1, and square root of 3 does not simplify. At this point, you could rationalize the denominator by multiplying by rad 3 over rad 3, and that would give me this fraction instead where the radical is in the numerator. But this won't be necessary for this problem. Now we want all angles x where the tangent is plus or minus 1 over rad 3. Let's investigate these one at a time. Let's explore where the tangent is 1 over radical 3. Tangent is sine over cosine, so second coordinate divided by first coordinate. Tangent is positive in the first and third quadrants. And at this angle, pi 6, or 30 degrees, second coordinate divided by first coordinate will be 1/2 divided by radical 3 over 2, which simplifies to 1 over radical 3. So this is one of the angles I'm interested in. The tangent will also be positive 1 over radical 3 at this angle, 7 pi 6, because negative 1/2 divided by negative square root of 3 over 2 will simplify to positive 1 over square root of 3. Also note that these two angles are in this interval from 0 to 2 pi, so I don't need to find coterminal versions of them. So these are the two angles and the only two angles between 0 and 2 pi where the tangent is positive 1 over radical 3. But we can also have tangent of x being negative 1 over radical 3. The tangent is negative in quadrants 2 and 4. And in quadrant 2, the angle we're looking for is 5 pi 6 because second coordinate 1/2 divided by first coordinate negative rad 3 over 2 will simplify to negative 1 over rad 3. And the fourth quadrant answer I'm looking for is at 11 pi 6. Because negative 1/2 divided by positive radical 3 over 2 will simplify to negative 1 over radical 3. And these are the only two angles between 0 and 2 pi where the tangent is negative 1 over rad 3. 5 pi 6 and 11 pi 6. So our final answer is that x can be any of these four angles. And these are the only four angles between 0 and 2 pi that satisfy this statement at which the equation is true. Now, confirming this with technology, I'm going to graph the two sides of this equation as if they were separate functions. So the left side I'll call y1, and the right side of the equation I'll call y2. I'll make both these graphs and look for points of intersection. All right, both equations are typed in. I'm just using y and y. Let me change my step size on the x-axis to pi, and then only look for points of intersection between 0 and 2 pi. If you want, you can crop the graph by putting curly braces next to the equation and saying that 0 is less than or equal to x, which is less than or equal to 2 pi. And this gives you a cropped version of this graph. If you click on either graph, the points of intersection with the other graph, the red horizontal line, are indicated. Focus on those x coordinates. We have intersection at x equals pi 6, 5 pi 6, 7 pi 6, and 11 pi 6. These are the four solutions between 0 and 2 pi. Moving on to the next slide. 2 times the secant of 2 alpha plus 1 is equal to 3, and we want to find all angles alpha that satisfy this equation where alpha is somewhere between 0 and 3 pi. That means over in this unit circle, we're going to rotate pi, 2 pi, 3 pi. Okay, let's isolate the secant of 2 alpha by subtracting 1 from both sides. You don't really need to keep the parentheses on the 2 alpha. Now I'll divide both sides by 2 to get rid of that coefficient. Now secant is the reciprocal of cosine, so we could change this to 1 over cosine 2 alpha must be equal to 1, and then multiply the cosine 2 alpha to the other side. So we're really looking for where this is true as well, where the cosine is 1. Now on the unit circle, that only happens at one position, the right side of our unit circle. So we take this argument 2 alpha, and let me start writing down different angles at which the cosine will be equal to 1. One angle is 0, the next angle is 2 pi. Then 4 pi, then 6 pi. Just keep adding 2 pi to keep rotating counterclockwise a full rotation. Or you can remove 2 pi as well, and so there's an infinitely long list of possible values of 2 alpha where the cosine will be equal to positive 1. Now we take this list and divide everything by 2 to isolate alpha. So negative 2 pi divided by 2 is negative pi. 0 divided by 2 is 0. 2 pi divided by 2 is pi. And then we get 2 pi, 3 pi, etc. If necessary, you must make this list as long as you need to ensure that you find all the angles that you are looking for given your restricted window. So I want to keep every single alpha in this list that is between 0 and 3 pi, including the 0. So 0 counts, pi counts, 2 pi counts, but excluding 3 pi. The 3 pi and on won't count. They're not in the window. Nor will any negative angle, because negative angles are not in this window. So the only values of alpha that we wind up keeping are these three, 0, pi, and 2 pi. Verify that all three of these satisfy the equation. Graph the left side of the equation as one function, the right side as a second function, and then look for points of intersection that satisfy this window. When I do so, I see what appears to be 4 points of intersection, but be careful that the fourth point here on the right is not included because 3 pi is excluded from our window of acceptable answers. So only these 3 points of intersection count, and they correspond to x being 0, pi, and 2 pi. Okay, let's go to the next slide. Let's do a quick review of solving by factoring and using the zero product property. This is something you learned in an algebra class. For example, if you have 3x squared is equal to 5x. Now, one temptation for students to do is to divide both sides by x, leaving you 3x equals 5, and then dividing by 3 and saying x equals 5/3. This is a solution. However, you've lost a potential solution by dividing by x, because when you divide by x, we're assuming that x is non-zero. Otherwise, you can't divide by it, which begs the question, is 0 itself a solution to this equation? And the answer is yes. Plug in 0 for x, and you get a true statement, 0 equals 0. So the best way to solve this is to avoid dividing by variables to cancel them. Instead, subtract the 5x and then factor. And then if ever you have a product of two things is equal to 0, then you know that one of the two factors has to be 0. So in this case, we do have a product. We have x times and then 3x minus 5. That must be equal to 0. So either the first factor is 0 or the second factor is 0. So we get two answers, 0 and 5/3. Okay, let's solve tangent theta equals 2 sine theta, where theta can be any angle between 0 and 2 pi. Let's begin by expressing tangent as sine theta over cosine theta. And now I'm going to multiply this cosine theta to the other side. Now I'll create a 0 on one side by subtracting 2 sine theta cosine theta from the right side to the left side. And now use factoring. Notice that each term has a sine theta. Factor it out, that leaves 1 minus 2 cosine theta, and then all of this is equal to 0. And now because I have a product, sine theta times 1 minus 2 cosine theta, and that product is equal to 0, therefore we can use the zero product property and say that either sine of theta has to be 0, or 1 minus 2 cosine theta has to be 0. So we get two different trig equations to solve. Well, using the unit circle, the sine is the second coordinate, and the second coordinate is 0, only at the right and left sides of the unit circle. So theta could be 0, could be pi, could be 2 pi, could be 3 pi, etc. Or we could even use negative angles, negative pi, negative 2 pi, etc. Of course, I'm only interested in these answers that are between 0 inclusive and 2 pi exclusive. So these negative ones won't count. 2 pi itself won't count because it's not in the interval of acceptability, and anything higher won't count either. So we only get two angles, 0 and pi. Now let's consider the second possibility. Add the 2 cosine theta to the other side, divide by 2, and now we're looking for all angles between 0 and 2 pi where the cosine is 1/2. Cosine is the first coordinate, 1/2 here for cosine, and a 1/2 here for cosine. Cosine is positive in the first and fourth quadrants. So the two answers I'm really looking for are pi/3 and 5 pi/3. Any other angle that's coterminal with these will not be in our window. For example, 5 pi/3 could be expressed as negative pi/3, but negative pi/3 is a negative angle, not in this interval. Similarly, pi/3 is a coterminal with 2 pi plus pi/3, which is 7 pi/3. But 7 pi/3 is again outside of this window. So my final answer will be, we can keep the 0 and the pi from the first factor, and then pi/3 and 5 pi/3 for the second factor. Let's go ahead and confirm this. The left side of my original equation I'm going to call y1. The right side, y2. We're going to graph both of these and then narrow our view to this window. Notice I'm not bothering writing y equals. You don't need to. You can just write the rule of the function and Desmos will graph it. Also notice I'm using x's instead of thetas. For graphing purposes, if you use x as the input variable, then Desmos will know what to do with it and graph it appropriately. Also, of course, make sure that when you're doing all of these graphs in this unit, that we are in radian mode. Let's go ahead and crop both of these graphs. Now look for points of intersection. It appears that there are 5 points of intersection, but the one that's on the right, the 5th one, that should be excluded because 2 pi is not technically in our interval of acceptability. So we focus only on these 4 points of intersection corresponding to x values of 0, pi thirds, pi, and 5 pi thirds. Okay, moving on. Now we have sine 2u equals cosine u. This problem presents some challenges because the argument 2u of one trig function doesn't match the argument u of the other trig function. So we have inconsistent arguments, which poses a problem when trying to solve trig equations. If this occurs, you need to find ways to use appropriate trig identities so that we can have all of the trig functions in terms of the same argument. Now, in this case, the easy way to do that is to use the double angle identity for sine. This was identity 17 on our identity formula sheet, and the sine of 2u can be written as 2 sine u cosine u. And now all 3 arguments are the same. They're all u. This will make solving the trig equation easier, and we will solve this much like we did the last example. Subtract cosine of u from the right side to the left side of the equation, and then factor cosine of u out, and then employ the zero product property. So either cosine of u must be 0, or 2 sine u minus 1 must be 0. So looking at the unit circle, the cosine is the first coordinate, and that is 0 at the top and bottom of the unit circle, corresponding to angles pi halves and 3 pi halves. And again, we are looking for only answers that are between 0 and 2 pi. So that's 1 counterclockwise rotation around the circle. Now over here, we will add 1 to the other side. Now divide by 2, and find all angles where the sine of u is 1/2. The sine is the second coordinate that occurs here and here, first and second quadrants. The sine is negative in the other 2 quadrants. And that corresponds to angles pi 6 and 5 pi 6. Now just combine these answers into one set, and I'm going to sort them from least to greatest. Pi 6 was the smallest, then pi halves, then 5 pi 6, and the largest is 3 pi halves. Again, I'll graph this, treating the left side of my original equation as one function, and the right side of the equation as a second function, and looking for points of intersection, but limited to this window. And we get this graph with these points of intersection. Look at the first coordinates, pi 6, pi halves, 5 pi 6, and then 3 pi halves. All right, let's go to the next page. Here we have the sine of w minus 3 pi fourths must be equal to negative rad 3 over 2, and w itself must be an angle somewhere between negative pi and 0, including negative pi and excluding 0. All right, so the trig function here is already isolated, but our argument is a little bit more complicated. This w minus 3 pi fourths represents a phase shift, so we're looking for angles w that after you remove 3 pi fourths, and then you do the sine of the resultant angle, then you'll get negative rad 3 over 2. Sometimes it's helpful when you have more complicated arguments like this is to do some sort of substitution. And let's solve sine A equals negative rad 3 over 2. Once we find all the angles A where this is true, and then we will then determine what the angles W have to be, and then we will limit our W's to this window. All right, so where are the angles on the unit circle where the sine is negative radical 3 over 2? It'll occur twice on the unit circle at the angles 4 pi thirds and 5 pi thirds. Now these are only 2 angles at which the sine is negative rad 3 over 2. They are the only 2 angles if you limit yourself from 0 to 2 pi, but if we do coterminal positions, we can get a variety of answers. Let's first explore the 4 pi thirds and all of its coterminal angles. If I add 2 pi to this, which corresponds to doing a counterclockwise rotation from 4 pi thirds, and since that's one full rotation, the resultant angle will be coterminal. So in my scratch work, I'm going to add 2 pi to 4 pi thirds. That's like adding 6 pi thirds. So adding the numerators only, we get 10 pi thirds. And add 2 pi to this, which means add 6 pi thirds, which means the numerator goes to 16 pi thirds. So the coefficient of pi is increasing by 6 every time. So once you pick up on this pattern, you can generate a lot more very quickly. If you start at 4 pi thirds and rotate one full rotation but clockwise, that's like removing 2 pi. And of course, 4 pi thirds minus 2 pi is equivalent to removing 6 pi thirds, take us to negative 2 pi thirds. Remove 6 pi thirds from this, so negative 8 pi thirds, negative 14 pi thirds, etc. in the negative direction. This whole collection, of course, are our quadrant 3 angles. So A could also be our quadrant 4 angle, 5 pi thirds. And to this, add multiples of 2 pi. So add 6 pi thirds, takes me to 11 pi thirds, 17 pi thirds, 23 pi thirds, etc. Or begin with 5 pi thirds and remove 2 pi. So 5 pi thirds minus 6 pi thirds is negative pi thirds, minus another 6 pi thirds will take us to negative 7 pi thirds, then negative 13 pi thirds, etc. forever. And these are our quadrant 4 answers. Try to put all these answers together, sorted, and it's not always easy to know how long of a list you should make. You can always add to it or remove from it, but I'll begin making my list with this negative 8 pi thirds, then this negative 7 pi thirds, so I'm increasing towards 0, then this negative 2 pi thirds, then negative pi thirds, then 4 pi thirds, then 5 pi thirds, then 10 pi thirds, then 11 pi thirds, then 16 pi thirds, then 17 pi thirds, etc. So here's a sorted list of all the different possible values for A, at which the sign is negative rad 3 over 2. The quadrant 4 ones in this list would be negative pi thirds and then every other one in this list. And the quadrant 3 angles would be 4 pi thirds and then every other one in this list. Now these are the values of A, and A represented W minus 3 pi fourths. So if I want to find the actual angles W that I'm after, I now need to add 3 pi fourths to all of these. So adding 3 pi fourths to all angles and demonstrating just one of them, negative 8 pi thirds, and add to it 3 pi fourths. I need a common denominator, so I have to multiply this fraction by 3 over 3 and the first fraction by 4 over 4. So I have negative 32 pi twelfths plus 9 pi twelfths, which gives me negative 23 pi twelfths. So here's the beginning of a list of consecutive angles, W, that will satisfy the equation. Now we finally shift our focus to which W's do we keep. And we keep only those W's that are between negative pi inclusive and 0 exclusive. So we only want to keep negative W's, so that eliminates all the positive ones I could generate. But what about these negative ones? Well, the next one in our list is negative 19 pi twelfths. Well, 19 twelfths is more than 1, so negative 19 twelfths times pi is going to be to the left of negative pi on a number line. So that's not in our interval either. In fact, the smaller I go, the further left we go on the number line. So it turns out that there are no W's in this window that will satisfy this equation. So this was a lot of work, perhaps for nothing. However, if I had widened this window, then perhaps we would have started including some of my options for W. But as it is, this has no solution, because none of my W's satisfy the condition that they be between negative pi and 0. Let's confirm this with technology. You can see that if you consider the entire function, that there are plenty of points of intersection. But if you limit your window to negative pi to 0, notice we do not have any points of intersection. Okay, let's go to the next page. Here we have only one trig function, cotangent of beta. Let's go ahead and isolate it by adding 3 to the other side, and then dividing both sides by 6, which simplifies to 11 halves, or 5.5. Now we're trying to find an angle where the cotangent will be 11 halves, but this will not be an angle anywhere on our unit circle. If you recall, cotangent is cosine divided by sine. If you explore all the points on the unit circle and do first coordinate divided by second coordinate, you will never find a result that is 11 halves. The unit circle is a limited tool, so we're going to need to use some inverse trigonometry. Let's go ahead and find one angle beta by using the arc cotangent of 11 halves. Now remember that the arc cotangent has a range of 0 to pi, so it'll give us a first or second quadrant answer. But because we're doing arc cotangent of a positive, we know that our angle will be somewhere here in the first quadrant. Reaching for a calculator, in radian mode, we get approximately 0.17985 radians, which is about 10.3 degrees. Now we're going to work entirely in radians, as we have been doing for this entire lesson, but I know this angle is roughly in this area right here. Now cotangent is periodic with period pi, and we also know that cotangent is positive in the third quadrant, because that's where tangent is positive. So if you're to rotate pi radians clockwise or counterclockwise, we get another angle. So let's do pi plus the arc cotangent of 11 halves, corresponding to a counterclockwise rotation from our first angle, which in radians is about 3.3214. Now notice, of these two options, consider our interval of acceptable answers which in decimal form, negative pi is about negative 3.14, up to positive pi, positive 3.14. So in decimal form, our radians have to be between these two decimals. I can see right now that this second one is too large, but this first one is just right. Are there other angles? Let's see if we can describe all of the possible betas. If we start with arc cotangent 11 halves, and to it we add multiples of pi, so adding pi once takes us to this third quadrant position, adding pi to that takes us back to where we started, and then continuing this, we'll just toggle back and forth between these two positions on the unit circle. Removing pi, subtracting pi is a rotation halfway around the circle, but clockwise, remove another pi, completes the rotation, and then continuing to remove pi will just toggle back and forth between these two positions on the unit circle. So if we start with arc cotangent of 11 halves and add to it any multiple of pi, where n is an integer, this will produce all of the possible solutions. If we were to actually write some of these out. So arc cotangent of 11 halves we'll use as our anchoring angle. Add pi to this, gets us to another angle at which the cotangent is 11 halves. Add pi to that, which is our anchored angle plus 2 pi, is another angle at which cotangent is 11 halves. Continue this forever to the right, and I can also remove pi, which corresponds to clockwise rotations halfway around the circle, and continue to remove pi's, so minus 2 pi, etc. in that direction. Now we've already established that the arc cotangent of 11 halves is between negative pi and pi. We've already shown that adding pi made it too large, so adding more will continue to make it too large. But removing pi, if I start at arc cotangent of 11 halves, which is about 10.3 degrees, and go clockwise pi, then I will stay within my window of negative pi up to positive pi. But if I rotate again another pi radians clockwise, I'll leave my window. Now in decimal form, I'll write down what some of these things are, and you can see why we are excluding these answers and these answers. And we wind up only including these two answers in the middle. They are the only two that satisfy this condition, that beta be between negative pi and pi. And we have our two answers. The first one was a quadrant 3 answer, and the second one I listed here was a quadrant 1 answer. Okay, let's check this one with technology. I'm going to graph the left side of my equation as one function and the right side of my equation as my second equation. Note that you could do something similar with this stage or even with this stage. I could graph cotangent beta as my first function and 11 halves as my second function. But I'll just go back to the original equation and graph those. So here's my cropped graph from negative pi to pi, and my horizontal line y equals 30. I do need to change my vertical scale, and then we can see 2 points of intersection. And these are precisely the two solutions that we found, measured in radians. Okay, next slide. Here we have sine 2v times cosine 2v equals 2/5. And v needs to be an angle between 0 and pi. Well, if this 2/5 was a 0, then I could use the zero product property and set sine 2v and cosine 2v separately equal to 0 and solve from there. But it's not 0, so I can't use the zero product property. Here I'm going to use trig identity 17, but backwards. This is the double angle identity for sine, and I can manipulate it by dividing both sides by 2 and saying 1/2 of sine 2 theta equals sine theta cosine theta. These arguments have to match, and if they do, you can condense this into sine 2 theta, double the angle. So using identity 17, we can write this as 1/2 times the sine of double 2v, which would be 4v, equals 2/5. Now I'm going to isolate the sine function by doubling both sides. And now I want to find all angles v where after I do 4 times v and then do the sine, I get 4/5. So we're actually going to solve this for 4v angles first. And again, 4/5 is not a ratio for which the unit circle is useful. But I do know that the sine is positive only in the first and second quadrants. So I know that 4v must be limited to such angles. So let's explore what the arc sine of 4/5 is. In fact, let's just call this specific angle alpha, which in radians is about, using a calculator, 0.927 radians, or 51.3 degrees. So I know it would be somewhere between 45 degrees and 60 degrees, roughly here. Now by symmetry, the second quadrant angle at which the sine is 4/5, we'll call this one beta, can be found by starting at pi and rotating clockwise alpha. So this beta can be found by doing pi and then remove alpha, which is about 2.214 radians. So my argument needs to be 4v, and I'm going to write down several angles for v at which the sine will be 4/5, keeping in mind that I'm only interested in the end in positive angles v. So I'm not going to explore any negatives in this case, but alpha is one such angle, and then the next one up would be beta. Now if I take alpha and I add 2 pi to it, that will be my next angle in my list, and then take beta and add 2 pi would be my next angle in my list. In this list, I'm sorting it as I write it. Then the next angle in the list would be alpha plus 4 pi, and then beta plus 4 pi, and then alpha plus 6 pi, and then beta plus 6 pi. And we could continue to keep this up as long as we need. And of course, there are some negative answers too, but we're going to ignore those because we know in the end we want v to be positive. So if 4v is any of these angles, where alpha and then adding multiples of 2 pi to it are my quadrant 1 answers, and beta and adding multiples of 2 pi to it are my quadrant 2 answers. Now, ultimately, I want to solve for v. So to find v, I simply take all these angles in this current list and divide all of them by 4. And so we get this list of angles. And it's no longer clear which quadrants we're in necessarily until I decimalize these. So reaching for a calculator and doing all these calculations, we get the following decimal versions. And now we want to keep only these angles that are between 0 and pi, which is 0 up to about 3.14. So yes, the first one we keep, the second one yes, third, fourth, the fifth one is too large, and after that will be too large. Let's check this one with technology. So the left half of my original equation, I'll graph that as my first function, and then the right side of the equation, I'll graph that as my second function, and then only focus on this window of x-coordinates. And we get these two graphs. Between 0 and pi, there's only 4 points of intersection, and the x-coordinates of these points of intersection are precisely the 4 answers I just found here. And this concludes our lesson on solving trigonometric equations.